Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. Selamat pagi.
Morning, Doctor.
Morning, Doktor.
Okay, sihat semua
Alhamdulillah sihat.
Are you okay?
Okey.
Okay. Shall we start now? Still in deflection. Beam deflection. We have done double integration method and then Macaulay method. Okay. If we have time, I can give another example. Also, if we have time, I'll give some example on class resolution method. Yeah. Today we have only one topic. Yeah. Method of unit load method. Yeah. Okay. Okay. So unit load method, as we have done. Yeah, as we have used the same method for truss analysis, yeah, which is based on virtual work principle. Yeah, what is virtual work principle is that external work is equal to internal virtual work. So it is used to determine the deflection and slope. Yeah, so this is the specialty of unit load method. Yeah, we can use also slope. Yeah, and it is also suitable for beam and beam with different cross section. Okay, yeah. So this is what difference between unit load method and also double integration method. Yeah. Okay. Because why? Yeah, it can be used for different cross section. Yeah, because it is split into different segment, similar to truss. Yeah, similar to truss. You remember when we are doing the virtual work method or virtual work method for truss. Yeah, we split into each member. Yeah, if there are, for example, 10 members. Yeah, then what are the sum of internal energy or internal work done on each member, and then we total up the sum, and then what is the work of external load virtual. Yeah, for example, in this case, this is the typical example in the last week lecture. If you want to know the deflection at point C, okay, then what you have to do is construct another structure, virtual structure. We imagine a structure that have the same deflection at point C, the same deflection at point C, delta, and then you see, and then we impose a unit load method, unit load method or virtual load here, and then calculate what are the forces in the member. So these forces is called virtual forces, and then use the principle of work of external load and work of internal load. P delta equal to U delta, where U is the member forces due to one unit load, and delta is the actual. Delta is the actual deflection in each member. This one, actual deflection. Okay. So using the same principle now, we use the same principle for beam. This, for example, to determine the deflection at point C and slope at point D. Deflection, this one is deflection, this one is slope. Slope is theta, deflection is delta. Theta is also, this theta is equal to dy dx. Deflection is y in double integration method. Okay, now because we want to know the deflection and slope, Therefore, yeah, we use two type of loading. One is one vertical loading for deflection at point C. Another one is unit moment. This one is unit load. This one is unit moment at point D, because okay, the question is point D. Okay, so a virtual unit load is applied at the point of deflection and in the direction of deflection at point C. Yeah, remember, in the direction of deflection. Yeah, in this case is in vertical direction. No matter whether it is downward or upward, but it is in vertical. If we found that it is negative, then yeah, it is downward. Yeah, similar to this one. And a visual moment is applied at point D. Visual moment is applied at point D. Yeah, so yeah, because we do not know what is the deflection, what is the slope, whether it is clockwise or anti-clockwise. Yeah, so we assume that it is clockwise, 1 unit load. Okay. Yeah. Yeah. Okay. Now for load, this one, for example, for vertical load. Yeah. Now 1 unit load is at point where the question asks for the deflection. Okay. External work equal to 1 unit load multiplied by delta. What is delta? Delta is the actual deflection. Understand? Delta is not virtual deflection, actual deflection. Okay. Deformation due to moment at x m, is d theta. Okay. Now, I go back to this one. Okay. In thrust analysis, what is work? Could work multiplied by the extension, deformation of each member, equal to force multiplied by extension or deformation of each member, because there is no bending moment. There is no bending moment. Okay. Similarly, in this case, okay, for the axial force, bending moment. So work is equal to, rotation. Rotation or deformation in terms of d theta. D theta, which form a radial here. D theta, it multiplied by moment. This is work. If d theta is equal to 0, there is no work done because moment is 0. Therefore, work is linearly increased with the moment. Work is equal to m d theta. M is the moment. Okay. Now, as we know, m is equal to ei d squared y over dx squared. This is from the curvature equation in the last lecture. Curvature equation. And d squared y dx squared is equal to d over dx multiplied by, in this bracket, dy dx. D squared y dx squared. But what is dy dx? Dy dx is the slope. Dy dx is slope. Y is the vertical deformation, and x is the horizontal axis. So dy dx is equal to d theta here. So equal to m. Therefore, d theta d theta over dx equal to m over ei dx. Okay, so this is the relationship between d theta and dx. Okay, and internal work, internal works equal to here m d theta. This one is m d theta is internal work in each small portion of small element. Now the whole structure actually is divided into many portions here. Many elements. We call it finite element. 1, 2, 3, maybe 100. Maybe 100. Similar to truss. This truss is divided into many member. In this case, how many member? Maybe 10 member. Maybe 10 member. And for beam, similarly, it is divided into maybe 100 member. You can use summation. You can use summation of 100 member. But if the relationship between x and y for this curvature is known, therefore we can use integration. If it is not continuous, or if it is not uniform, or if there is no formula of this curvature, then we have to split into each member. Then we use summation. That's the difference between summation and integration. When you know the equation, we can use integration. If we don't know the equation, then we use summation. Then we use table, as we have done in truss. And this is mathematics. I hope you can understand this basic method of mathematics. Numerical integration. If I'm not mistaken, you have done this one in mathematics. Okay. Therefore, I'll say, I have explained what is meant by integration. Integration is actually summation. But integration is used for any continuous function, which can be derived mathematically. But summation is when there is no continuous function. Okay, and then we use external visual work equal to internal work. 1 delta equal, and this one is for delta, for deflection. This one for slope. So deflection equal to m, and d theta equal to m. M is for actual moment, and m small letter is for moment due to unit load, and m theta small letter is for moment due to unit moment. Okay. Why it, sorry, this one. Yes, correct. Why it is d theta? Because d theta equal to m over ei. Okay. Read here. M delta bending moment due to virtual unit load at point C. M theta bending moment due to virtual unit at point D. In this case, in this case, it is required to determine the deflection at point C and slope at point D. If this deflection and slope to be calculated is at the same time, at the same point, then you apply one unit load at the same point. Okay. So this is the derivation. This is the derivation. Now, we go to the application. Yeah, you straight to the example. Okay, unit load method. Sorry. This is not in your note. This is before we go to the actual example. I introduce this basic example which I have given to you for double integration method and also for Macaulay method. Then you can do it yourself, comparison between each of the three methods for this one unit load, one point load at the midspan. And you'll find that the final answer will be the same. Okay, then I hope it can make you understand better. Okay, determine the deflection of the beam at midspan B due to load W. EI is constant. EI is constant. Okay. Now this is actual structure where reaction at A and C equals to W over 2. Simple because this is symmetry. And for the virtual structure, we apply point load at the point B where, for which the question is, the question is at the point B. Okay. And due to 1 point load, the reaction is 0.5 and 0.5. Now what next? Okay. Okay. The energy or the work done in this member is equal to, actually, if you split into 100 member, 100 element, then you sum up this element, then you can get the total work split into 100 element, because we know the equation of the bending moment due to unit load and due to actual load. Do we know the equation of bending moment? Yes, it's very simple. This is the equation. Okay. Now, we just split into two elements or two sub-elements or two segments, AB and BC. Why we have to split into two segments? Because moment equation AB is not similar to moment equation for BC. Two continuous function. So in this case, we split into two. Right side. For the left side, moment between A and B is equal to W as 0.5 Wx. This is for actual, and M equal to 0.5 X. This one for virtual. Now, if we go to BC. Okay, what is the moment here? The moment equation is equal to what? W over 2 multiplied by X minus W multiplied by X minus L over 2. Actually, I include the equation, but I delete the equation. But since AB and BC is symmetry, similar to unit load, AB and BC is symmetrically loaded, and also symmetrically structured. Therefore, energy work at AB and BC are equal. Similar to the virtual load method, virtual structure, AB and BC is equal. If this unit load method is applied eccentrically, maybe somewhere here, then work at this segment and this segment is not equal. That one different case. Okay? But in this case, it is equal. Yeah. Also start this moment. Yeah. Start the moment equation. This one. From this one from right. Sorry, from left. This one we develop the moment equation from right support. This one from right support. What is the purpose? The purpose is so that the moment equation does not include this point load. If you start from left, then you have another term. But if you start from right, you have only one. If you start from left, then it will become complicated. And you can try at home. If you start from left, it will become complicated. I have tried this one, this equation. Therefore, you can see here, okay, but for moment between AB, use this sign convention. Yeah, you can refer to topic 1 on bending moment diagram and shear force diagram. Yeah, if we start from right support, we use clockwise positive. If we start from right support, then we use anti-clockwise positive. Then you have similar, yeah, similar equation. And then, okay, this one is for AB, this one for BC. AB and BC. Yeah, but actually, AB and BC similar. Therefore, yeah, multiply by 2 for any part of AB, BC, and you solve this equation. Yeah, I don't have to show in detail. Yeah, you can work out yourself. Yeah, we end up with delta equal to WL to the power of 3, 48 EI, and it is proven that it is similar. Yeah, the same answer in double integration method and Macaulay method. Okay, so we have three methods. Okay, will give the same answer. Yeah, if we use the other method, moment array method, yeah, it will also, yeah, give the same answer. Okay. Any problem? Yeah. It's quite difficult to ask. Yeah, to ask question. Okay, as I mentioned just now, the beam and loading are symmetry, so we consider only half and double the work done. Yeah. So actually, this part, you can just neglect. Yeah. Because this part and this part is equal. Okay. Now, so I use the same maximum deflection at mid-span. Mid-span here, what is what is the maximum deflection? As we know, the slope at mid-span is equal to 0. Yeah. So you don't have to calculate it. The slope is 0. Okay. So understand what is mean by the slope. So again, we have actual structure, we have virtual structure. Yeah. For actual structure, reaction is equal to W multiplied by L divided by 2. Yeah. And moment along AC is equal to M WL over 2x minus WX squared over 2N. Yeah. For virtual structure, reaction at support due to 1 unit load is half and half, 0.5, 0.5. Yeah. And you see here different bending moment, but we know the equation. Yeah, the equation of this curve is this one. This is the equation. That's why we can use integration. If we do not know the equation, we cannot use integration. We have to use summation, numerical integration. Yeah, similar to moment AB. Yeah, you see here m equal to 0.5x linear equation. Yeah, linear equation. You see here straight. That means it is linear. This one is parabolic. Yeah, because we have squared here. Okay, what next? Okay, so again using this virtual work principle, delta C equal to summation between L and 0. Between L and 0. When summation integration, when it is integrated between L over 0, that means we can integrate half of the beam and then multiply by 2 here. Yeah, integrate half of the beam L over 2 here, but multiply by 2 because we know that the energy or the work done at each segment are equal. Yeah, so this is the equation now. This one is M due to actual load. This one is M small letter due to unit load. Yeah. Okay. Now solve this equation. Yeah. Solve the equation WLX over 2 multiplied by X over 2 minus WX squared minus multiplied by X over 2. Then you got here WX to the power of 3 divided by 4 and so on. Yeah. So simplify integrate integrate this equation WLX power of 3 and so on, and finally this is the integration and integrate between L over 2 and 0. So this is quite long long calculation, but I just simplified here. You got 96 256 and then 96 256, and then at the end this is the answer 5 over 384 proven. What is 5 over 384? We have proven that it is the same answer, the same answer with the ones that we have got from double integration method and Macaulay method. I think I have shown to you the Macaulay method and double integration method for this UDL. And I also have remind you that this formula is very important. The basic formula for deflection of UDL 5 over 384. But I think if I'm not mistaken, for the point load, for the point load, I have not shown to you the method of double integration and Macaulay method. So you have to do it yourself, but I can show you, but we have no time. It is in this slide actually. Okay. Now, what next? Okay. Example 8. Calculate the vertical deflection at point C of the beam. Take E equal to 200 and I equal to 6,000. Okay. Now, E and I is uniform. If E and I or EI is not uniform, yeah, we can still get the answer from this unit load method. Yeah. Okay. The support reaction MA, yeah, RB equal to 60 kilonewton, yeah, and RA equal to 80 kilonewton. And this is the bending moment diagram. Yeah, but this bending moment diagram is not important. You don't have to draw the bending moment diagram in the exam. This is just to show you and just to make you aware, and you have to familiar with the bending moment diagram. Yeah, this very simple. Yeah, simple loading condition. And 480, what is 480? 480 equal to 80 multiplied by 60, and 480 here is equal to 60 multiplied by 80. Reaction here. Yeah, is very basic. Yeah. Okay. The question now is vertical deflection at point C of the beam. This point C. Okay. Now, why we need to split into three? Yeah, we need to split into three segments, and we have to develop bending moment at this point, and at this point. And this bending moment, when you develop the bending moment equation, you can start from left or you can start from right. Yeah, whichever you feel convenience. Yeah, but normally we start from left support. Okay, so from left support, this one also from left support. Okay, for this one, you can start from left support. But how many loading now? 1, 2, 3. 3 loading. If you start from right support, you only have 1 loading. It is shorter. Why you must choose the shorter one? Because, yeah, as you see here, in unit load method, yeah, it involves two moment equation, multiplication of two moment equation. So if this moment equation, yeah, you wrongly choose the long one, then it will becomes very long equation. Therefore, yeah, in this example, yeah, for this segment, the moment equation is based on starting from right support B here. This one, unit load. Okay. Now for unit load method. For unit load application. So the question is point C. Therefore, apply unit load at point C. Remember, unit load is applied at the point of question. Here. This is the bending moment. But this bending moment diagram is not important. Yeah, you don't have to draw the bending moment diagram in a test or exam. Yeah, it just make you known and aware or remind you. Yeah, what is the bending moment diagram? Yeah, okay. 0.75, 0.25. And remember, this one simple equation or simple loading condition, simple beam or structure condition, you don't have to use or to calculate using this long equation. This is short. This is short equation. But still can consider long when you have another shorter version, simpler version of equation. Okay, just by ratio. What is RA? RA is equal to 1 multiplied by the longer distance divided by the total distance, and RB is equal to 1 multiplied by the shorter distance divided by the total distance. And make sure that RA is larger than RB because the unit, the load is very close to A. Load is closer to A compared to B. This is it's not common sense, but how to check your answer whether it is sensible or not, because it is important that it is impossible that when the load is closer to A, but reaction at A is smaller compared to B. It is not not possible. Okay. And apply the equation delta C equal to mm over EI. M is the moment due to actual structure, and M is the moment due to this unit in virtual structure due to unit load. Okay. And delta C is equal to the actual deflection, the value that we have to calculate now. Okay. Okay, now you have three, you have three segments: AC, CB, AC, CD, this is D, and DB. Therefore, you have three segments here. Therefore, you have three segments here. Why you need to split into three segments? I repeat, because the loading is not symmetrical. The loading is not symmetrical. Therefore, you have to split into three segments. Okay. For segment 1 is between 0 and 6. This one segment 1. This one segment 2. This one segment 3. Segment 2 is between 6 and 16. And segment 3 is between 16 to 24. Or, in this case, for this two segment, we start the bending, the equation, derivation of the equation of moment from the left. But for this third segment, we derive the bending moment based on, we start from the right. From the right. When you start from the left, you use the sign convention, anti-clockwise positive. When you start from right, you use the sign convention, clockwise positive. This one clockwise positive, this one anti-clockwise positive. Okay. So segment 1, M equal to AT multiplied by X here, and M small letter 0.75 multiplied by X. There is no loading. Okay. And then for the second segment, M equal to ATX minus ATX minus 6 for AT, and so on. And M this one. And for the third segment, we start from right. Start from right. M equal to 60X and M virtual, due to unit load equal to 0.25X. You can try if you start the equation, or if you start the derivation M from left, it is much more longer than this one actually. Yeah. So yeah, better to yeah be clever. To be clever. From which point we start in the derivation of the bending moment equation. Okay, no problem, eh? Okay, now, now use the principle of yeah energy. Yeah, this is unit load method. Delta equal to mm over ei dx. Here is m, small letter m, capital letter M, capital letter yeah, letter M, and sorry, capital letter M and small letter m. And this one also capital letter and small letter. Yeah, I check. Yeah. This one is equal to 480. Yeah, 480. 480. Okay. Okay. Hmm. Correct. 480. Okay. Yeah. Uh, Integration of this equation here. This one integration. Yeah. And the first is integrate between 6 and 0. This one is integrate between 6 to 16. And this one is integrate between 16 to 24. Or in this case, 0 to 8 from right. Understand? This third segment, actually, this is integration between 16 to 24. Yeah. If you start from right, yeah, but sorry, you start from left, yeah, but because we start from right, then the integration is between 0 and 8 meter only here. Yeah. We start from right, so integrate between 0 and 8 from right. Okay, and you solve the equation, yeah, you get 0.0187 meter or equal to 18.7 millimeter deflection. And for this example, yeah, actually, yeah, maybe you can do your own homework, at home. If you are required, yeah, to calculate the slope at point C, this one is the deflection, the slope at point C. I hope you can do it. This is not the the example question. Just to do some exercise. Yeah, the slope at point C. Okay. So yes, I think yeah, yeah. This is the last example on unit load method. Yeah, we have only 3 example here. Yeah. Uh, and we are not going to discuss on moment array method, but maybe we can share some slide here, but it is not our scope for this semester. So, yeah, so this is the end of the topic on beam deflection. So I think the end of example, because yeah, I I go through some another example on deflection using double integration method and also trust analysis. So we will have short break about 5 minutes before we continue to the second session. Second session is on revision. Revision. Or if you have any question, you can ask now. I'll check again your attendance. And I think uh, I've not shown you this slide before. You're using Macaulay method. Okay. Mx equal to W over 2x. This one for segment AC. Segment AB. First segment. And then moment at any point along segment CB here. Second segment. Sorry for this error. Equal to Mx and so on. Okay. Now, if you combine this equation for the whole segment, for the whole span, between A and C, then this is the equation. But remember again, I repeat, in this equation, when x minus L over 2, this one minus, x minus L over 2 is negative, then you neglect this one, cancel this one. Remember? If this one is positive, then we can consider into the calculation. Okay. Okay. So this is the equation. Mx equal to ei d squared y dx squared equal to this one. This is the first segment. This one for the whole segment. Okay. And this is the formula. This is the integration of the slope and also the slope and deflection. So we have two unknown. Two unknown. Okay, C1 and C2. Then we apply the boundary condition. The boundary condition. When x equal to 0, y equal to 0, this is the boundary condition. Then C2 equal to 0. When x equal to L and y equal to 0, this is the boundary condition again, 0 equal to and so on. Okay, and therefore C1 equal to WL squared over 16. And I don't have to go into detail. We got here EY maximum at point C equal to WL to the power of 3 divided by 48. And it is proven that it is similar, equal to what we have done using unit load method just now. So this is Macaulay method. Okay. I check if there any example that has not been shown to you. Okay. Okay, enough. Okay. And then this one for beam deflection. Now I think we have finished beam deflection. Unless if you have any question. I don't know whether I can. Maybe before we go to the revision on thrust equation, on thrust analysis, I want to go to first assignment. Assignment Macaulay method. I check. Let's check. Whether I have the assignment or not. Sorry. Mm. Mm. Sorry, I misplaced the assignment for deflection. Um, yeah, sorry, tak boleh nampak skrin. Sekarang you nampak skrin tak? Oh, tadi saya tengah cari file. Okay, saya pergi ke Trust dulu sekarang. Yeah. I'm trying to explain or briefing on to give briefing on beam deflection actually. Yeah, but I couldn't find the file. Maybe I misplaced the file. Yeah, which folder? Yeah, because the beam deflection is assignment using Macaulay method. You have to submit. Yeah. I try again later. But this one, I want to just give some revision. Yeah, revision on trust analysis. Yeah, on trust analysis. Okay. 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 Fortunately, I got this slide. Okay. Okay. Can you see this slide? The problem is a truss applied 400 kilonewton at point B and point D, and this truss is supported at point C and point A here. Point A is roller support, point C is pin support. Okay. Now we are going to calculate, to analyze this truss, the member forces, not the deflection. Okay. First is to determine the determinacy of the thrust externally and internally. Externally, you just use or check the number of reaction. Simple. If the reaction is equal to 3, then it is determinate and stable. If reaction is less than 3, then it is not stable. Yeah, not stable, but determinate. If reaction is more than 3, 4, 5, or 6, then it is not determinate or indeterminate externally, which means we cannot calculate the reaction because the number of reactions are more than 3. Why? Because the number of equation for rigid body, yeah, equilibrium is 3. What is that 3? Summation fx0, summation fy0, summation m equal to 0. Only 3. If there are 4 reactions, then it will be indeterminate. Yeah, or we call it redundancy. Yeah, 1 degree of redundancy. That one external. Yeah, just repeat actually. Yeah? Okay. And then for internal determinacy, okay, this is to check the number of member, yeah, in relation to the number of joint and also reaction. Why comes this formula? M equal to J minus 3. Why not 3J? Why not 4J? Yeah, it has been explained in last week. Okay. Now this is the formula. Yeah, if you couldn't understand, the derivation is formula, we just memorize. Yeah, it's not easy to memorize. M equal to J minus 3. R is reaction. J is number of joint. M is number of member. There are 3 reaction. 4 joint, 1, 2, 3, 4, and 5 member. Is 2j minus 3 equal to 2, 4. It is okay, and it is called determinate internally. Determinate internally. And then we can proceed. Yeah, we can proceed now. But, okay, one question. If it is externally indeterminate, for example, R equal to 4, can we find the force in the member? Maybe can, maybe cannot. Yeah. In some cases, we can find the force in the member, even though the reaction externally is indeterminate. Yeah. But not in all cases. Okay. So generally, we can say indeterminate if reaction is more than 3. Okay. Then the first step is what are the reaction at the joint? Yeah. MZ0, FX0, FY0. This is what I mentioned just now as rigid body diagram. Yeah, this one is rigid body. Rigid body equilibrium equation 3. Yeah. So from this equation or from this rigid body equilibrium equation, we have RA 600, RC 200, HC 600. Okay. Now this is the answer actually. Yeah. One of your friend asked me the answer for the tutorial. So I have not having that answer for tutorial. Yeah, but this is the answer. And how to get this answer? How to get this answer? Using what? Yeah, you can use joint method or you can use section method, or you can use what resolution method, or you can use what I call it as resultant method. There are four methods. Now I give you the third method, resolution method. Okay, resolution method. Okay, so this is now the force, external force or applied force, and the reaction. This is reaction. Make sure just simple to check. The applied force is 600 horizontally, so in your reaction it should be equal to 600. The total force, the total vertical force is equal to 400. So make sure that the total reaction is equal to 400 in opposite direction. Opposite means 600 in upward direction minus 200 in downward direction. Then it is now balanced. 400 upward, 400 downward. That reaction. So what next? Okay. What is the shape or the slope of the slanting member here? This one 4, this one 3, therefore 3, 4, 5. 3, 4, 5. What is this? This one 3, this one 4. So similarly, 3, 4, 5. Why it is important? Because if we use this ratio, ratio of this triangular, this is actually theorem Pythagoras, to find the rectangular component of each member. Okay, so what first step now? Okay, similar to join, similar also to join method. Which join we want to start? Which join we want to start? We want to start from the the most easiest join, and we cannot start from the join that it is impossible to solve the problem. For example, can you start with join B? Cannot, because there are how many? 3 members. 1, 2, 3. 3 members. More than 2. Can we start from member D? 1, 2, 3. Also cannot. Okay. Can we start from join A? You have 1, 2. If you use join method, yes, you can start from join A. If you use resolution method, you can only start from the join, connecting two members only if one of the member is in X or Y direction. If both member are slanting means it is diagonally, you cannot start from A. This is resolution method. But for join method, okay. But for resolution method, you must start from the join where at least one of the member are horizontally or vertically. Look at C. Both members are, one is vertical, one is horizontal and another one is vertical. Therefore, it is very the most easiest one to start. So now we start from C. Okay. Now this member, this member BC will develop or will induce internal force which in opposite to 600 and this member CD, since it has no other component, yeah, because this is a vertical component, so the force in this member should, yeah, oppose or counteract this reaction. Therefore, 600 easy. And what next? So okay, when this is 600, yeah, because this member should be in equilibrium. Therefore, when you have 600 right direction, you must have another 600 in left direction. Yeah, to make this member in equilibrium. Yeah, yeah, there are two conditions. Yeah? The joint must be in equilibrium and member must be in equilibrium. For equilibrium of joint Fx0, Fy0, for equilibrium of member or rigid body diagram, Fx0, Fy0, and moment equal to 0. Okay. And what next? Yeah, you have 600 years. So, and then this one, 200. Yeah, 200. Yeah, to oppose this 200. So when it is 200, what next? This one, 200. Okay. Two member now settle. So what next? Yeah. Where you want to go now? You going to B or going to D? Can you go to B? Yeah. Now, if you go to B, yes, correct. You have two member. Yeah, two member is okay. That one for joint method. But now for resolution method, yeah, uh, it is possible, but you have to write the equation here. Yeah, fx0, fy0. But now we don't want to write equation. Yeah, you want to do it, yeah, on the spot. So for resolution method, when you have both of the members are diagonally slanting or having rectangular component x and y, this one x and y, we cannot go to that joint. Understand? You can go to the joint if you use joint. Yeah, if you use equation. Yeah. So yeah, the best choice is to go to D, because if you go to D, you have two member here. Yeah. And only one member got rectangular component in X and Y, and AD has no rectangular component, only horizontal component. Therefore, now you go to D. Okay. But yeah, uh, you should understand also. Actually, you can start from A. Yeah. If you want, if you don't want to go to D, you can start from A also. Yeah. But now, yeah, let us start from A. Okay. Yeah. You can go to D or you can go to A. If you go to D, then you prove the answer is correct when you come to A. If you go to A, then you have to prove the answer is correct when you go to the D. Okay. Now we go to A. It is 600, therefore this one is 600. Yeah. And yeah, take note here. The length of this horizontal and this vertical is in proportion or in reasonably correct ratio with this one. Yeah. This one is shorter than this one. So that, yeah, the resultant, yeah, the resultant or the combination, the vector combination of this arrow is in line with this member. So when you draw this arrow, make it sensible enough, to show that it is not 45 degree. Okay. Now when it is 600, what is this? Yeah, this one is in ratio. What ratio? 600 multiplied by 3/4. Yeah. This one 600. What is this? If this one is 4, what is this? This one should be 3. Yeah. Because uh, the angle is already given. So if this one is 4, this one is 3. So if this one is 600, this one is 450. How to get 450? 600 multiplied by 3/4. Yeah, 3 is the distance of this component, and 4 is the distance of the force here, 600. Okay, so when it is 600 and 450, yeah, there must be force here so that it becomes equilibrium. Oh, you go to here first. Here, there must be force here so that it is in equilibrium. Yeah, so 450, this one is should be 450. When this is 450, then it should also be 450. And what next? Yeah, uh, so yeah, to make this member to be in equilibrium, therefore you must have another 600 and 450. Okay, then okay, so you have what BD, yeah, BD. Okay, now what next? When you have 150 here, sorry, 450 here, yeah, the component, rectangular component of this member should be, yeah, made these two forces are in equilibrium. Therefore, to make it equilibrium for this joint, so you have 450 here, you have 600 here, so you must have another 150 to make this joint equilibrium. 150. So when this is 150, what is here? 200 in proportion or in ratio. So, and then when you have 200 here and 150 here, so what next? Easy. Yeah. Just put another force in opposite direction. Any other member now? No member. Yeah. Now we have not gone to this joint. Yeah. So now check this last joint whether it is equilibrium or not. Yeah, whether it is equilibrium or not. How to check? Okay, in x direction, you have 600 here, you have 450 here, you have 150 here. 600 negative, 450 positive, 150 positive, 450 plus 160, 600. Okay, then it is equilibrium in x direction. Okay, in vertical direction, we have 600 here, yeah, you have 400 downward, 200 downward, 400 plus 200 equal to 600. Therefore, it is balance or equilibrium. So complete. Yeah. So next, what is the actual force in the member? This one is component, yeah, rectangular component. What is the force in this member? Yeah. So using the theorem Pythagoras, yeah, again, yeah, the force in this member is equal to square root of 450 squared plus 600 squared. You got what? 750. This is the answer. Yeah. This one is not answer. This is the answer. Yeah. So in the exam, you cannot show, yeah, this value. Yeah, you have to show this value. Okay. And what's about this one? 250. What is 250? Yeah, square root 200 squared plus 150 squared. Okay. Hmm. I know newcomer, Zimin. But you are in not in my list. Uh, anyway, welcome. Welcome to my lecture. Okay. Just to remind you, yeah, this is the third method. I have another fourth method. Fourth method is I can straight calculate this 250. Yeah. Okay. For this third and fourth method, using resolution method and using resultant method, yeah, you cannot use or present in the exam or in the test. This is for design or next year. Yeah, in the exam you can only use I don't know about Dr. Yunus because Dr. Yunus is in charge of the exam. You can only use joint method and resolution. Section method. Yeah, you can use this method, but you have also to show the equilibrium equation. Okay, and you can use this one for just to self check. Yeah, the equation, maybe you can develop the equation based on this uh, simple method. Okay, uh, this is the answer. Okay, so that's I give you one, yeah, extra example today. Yeah, any question? I still try to find the file for tugasan and assignment. I try. So far, any question? Any question on truss or beam? If you have any particular example, I can repeat again or I can revise. Yeah. Otherwise, yeah, give me time to find the word file. I don't know where is it. Can you see me now? I'm now searching for the file. Maybe you cannot see me or you cannot see the slide. Yeah. Wait. Wait for a moment. Sorry, it takes time, eh? Can you see the assignment now? On my screen, I show assignment 01. Can you see the assignment? Yeah? Ada nampak tak? Tak nampak eh? Ya ya. Okay, now can you see the slide now? Yeah, ada?
Yes.
Ada.
Ada? Okay.
Ada.
Sorry, because I'm not familiar with the Webex ni. Now what I'm doing now is just using print screen, yeah, the PDF file, yeah, and then I copy and paste into the slide, yeah. Okay, yeah, this is the assignment. By using Macaulays method, determine the deflection at point A. Okay, deflection at point A, yeah, which of course the maximum deflection at cantilever. Determine the deflection at midspan of BE, midspan of BE. Determine the slope at point E, point E, yeah, here, point E. Determine the position X and value of the maximum deflection. Yeah, maximum deflection. The maximum deflection can be maybe A or maybe, yeah, somewhere between B and E. Yeah, there's another deflection. Okay. Sketch the elastic curve for the beam, mark and label all the important value in the diagram. And yeah, it is mentioned here using Macaulays method. Okay. Now, first of all, I hope you can, yeah, you can imagine what is the shape of the deflected beam. Yeah, what is the shape of the deflected beam? Yeah, you will have one here. Okay, and then maybe somewhere here, and this is the shape. Yeah, I hope you can see here. Okay. Okay, this is the shape. So at one point here, yeah, there is a maximum deflection, but we do not know. Yeah, because if it is symmetry, then we know that maximum deflection is at its span. And here A, yeah, it is of course, yeah, maximum deflection. Yeah, but this one is at overhang or cantilever. Yeah, and also at this point there is one point of here. What is the deflection point A? Okay, deflection at midspan of BE, we do not know. The slope at E, yes. At E, the slope is maximum, but we don't know what is the slope. Okay, and in between B and E, there is a point, yeah, where the slope is equal to 0. Yeah, the slope is equal to 0, and yeah, I'm sure, yeah, the point where the slope is equal to 0 is the point with maximum deflection. Okay, so how to determine the deflection at midspan of BE? It is simple. Yeah, just, yeah, you have 3, 4, 2. Yeah, 3, 4, 2. That means 4, 2, 6, 9. Yeah. So at midspan of BE is means at 4.5 meter from B. Okay, so it is easy. Okay, just replace or substitute x equal to 4.5 meter to the Macaulay's equation, then that is the maximum, that is the deflection at point at midpoint. Okay, now determine the slope at support E. Also easy. Yeah, you just substitute x equal to 11 meter, and then you can have the point the slope at point E. Or if you start your moment equation, start from E. You start from E, then you can use x equal to 0 to find the slope at point E. What I mean is the slope equation. This one you use deflection equation. For D you use slope equation. Okay. When you are deriving the slope deflection, the slope equation and deflection equation, you will have to solve unknown C1 and C2. And for that one, you use boundary condition. Boundary condition. Your boundary condition is at B, deflection equal to 0, and at E, deflection is equal to 0. And you do not know at which point the slope is equal to 0. Okay, that one's boundary condition. Okay, E, determine the position X and the value of the maximum deflection. The position X and value of the maximum deflection. Okay. Now, between B and E, we have maximum deflection. You have to understand. This E. The question for E is not maximum deflection at overhang. If we ask you the maximum deflection at AB, for sure, A, but between B and E, we do not know. Okay, so what we can do is that you try 1 point or 3 point here, 1, 2, 3, or maybe 2, the more is better, and then what is the deflection, and then you use interpolation, to find what is X value for the deflection equal to maximum. Interpolation. Therefore, for interpolation, I think you need at least three. Maybe somewhere here, somewhere here. And what are the deflection? That's the method. I don't know. Maybe you have another method, mathematical method. In mathematics, actually, you can have another choice. But I'm not sure whether we have another method or not. Okay, and then sketch the elastic curve of the beam. This one sketch. But remember, when you do sketch, we also must have some idea, sensibly enough to represent the sketch. It's common sense. Okay, and mark and label all important value in the diagram. So, okay, to me, the only part that need you to work more, to spend time, is E value. E section. Determine the position X and value of the maximum deflection using Macaulay's method. Okay, and this question is specifically requested from Macaulay but you are also encouraged to do it yourself using unit load method. Yeah, unit load method. Yeah, and also you using double integration. Yeah, from there you can prove. Yeah, you can prove by using unit load method. You can prove that your answer is correct. Then you can submit. Yeah, with very confident. Okay. Yeah, I think it's clear. Any question? I don't know about this assignment whether it is group assignment or not. Yeah, but yeah, I think because we are in, all of you are at home. I think it is individual assignment. Yeah, and I also not sure what's the date for submission. I'm not sure. Yeah, maybe I'll try. I'll ask Dr. Yunus, or maybe Dr. Yunus have inform you the date of submission. Okay. Yeah, so this is my college method. Yeah, and maybe uh, some of you may ask us for what method to be used in final examination. Yeah, whether Michaelis method or double integration method or unit load method or moment method. Yeah, and that's one. Yeah, I'll answer to you. Yeah, during the revision weeks. And there is no revision week. Yeah, but I hope we have time. To sit down this in online. Maybe 1 or 2 hours before in last week. Last week, maybe last week is before Chinese New Year. Maybe first week of February. First week of February. Next week will be another topic on column. So next week is the last week, and then we have another. If I'm not mistaken, we have another week before examination. Yeah. Okay. So for that, thanks for attention. Yeah, and thanks for attendance. Yeah. If you have any question, you can ask me now. If not, we can leave this meeting. Okay. Question? Or some of you write WhatsApp message to me. Yeah. Also possible. Yeah. You can also email to me. Yeah. But before you email, after you email, you must write message to me. Yeah. Because I'm not opening email all the time. Okay. Yeah. Thank you. Yeah. And see you again next week. And don't forget, the test one will be on. The test will be on 24 Sunday night. Okay. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Okay. Thank you. Thank you. Oh, kabinet sudah ada kan?